you're falling. Not floating. Falling fast, and there's no ground beneath you. No ground anywhere. Just thicker and thicker gas closing in around your ship like a fist. You check your altitude. It means nothing here. There's no surface to measure against, no down that leads anywhere except deeper into a planet that doesn't have a bottom. You're 1,000 kilometers into the atmosphere, and the pressure outside your hull is already higher than the deepest point in any ocean on Earth. And you're still falling. For most of your life, you probably pictured landing on another planet the same way you picture landing on Earth. A parachute deploys. Wheels touch rock. A flag goes up. That's how we got onto the moon, onto Mars. It's the picture every space movie sells you. But Jupiter has no rock to touch. There's no surface anywhere inside it, not at any depth, not under any amount of pressure. You could fall for thousands of kilometers and never hit bottom. Not because you haven't gone deep enough, but because there is no bottom to hit. So if landing has always meant touching solid ground, what does it even mean to land on a planet that may not have any? That's what I want to show you. Jupiter isn't a rock with weather on top. It's almost entirely gas and fluid, stacked thousands of kilometers deep, with no solid surface at any layer scientists have been able to identify. Earth has a crust you can stand on. Mars has dust you can drive across. Jupiter has hydrogen, and hydrogen all the way down. Here's the part that gets me. We're used to thinking of ground as a guarantee. Every planet we've ever sent a rover to has had one. Jupiter breaks that assumption completely, and most people have never had to think about a world that simply doesn't offer you a place to stand. So how do we actually know what's down there if no spacecraft has ever survived deep enough to find out? In 1995, NASA's Galileo mission dropped a probe directly into Jupiter's atmosphere. It transmitted data for 57 minutes before the heat and pressure destroyed it, at a depth of roughly 150 kilometers below the cloud tops. That's the deepest direct measurement we have, and it didn't even come close to a surface. Now, some of you are thinking, maybe it just didn't go deep enough. Maybe there's rock further down, like Earth's core. Fair question. The answer comes from physics, not assumptions. As you descend, the hydrogen gas gets compressed under such extreme pressure that it stops behaving like a gas at all. Around 13,000 kilometers down, the pressure becomes so intense that hydrogen is squeezed into a liquid metallic state, a phase of matter that conducts electricity like metal but flows like a fluid. Scientists at Lawrence Livermore National Laboratory recreated this exact transition in 1996 using diamond anvil pressure cells, confirming hydrogen really does change into metallic liquid form at pressures Jupiter reaches naturally. There's no clean line where gas becomes liquid, becomes solid. It's a gradient, a planet-sized soup that gets denser and denser with no clear floor, only thicker fluid, all the way to a core that may be partly dissolved into that same fluid. And here's the important part. Even if you somehow built a ship that didn't melt, didn't get crushed, and didn't lose radio contact, there's still nowhere to set it down. Most people picture cavemen. Most people picture astronauts on Jupiter the way they picture astronauts everywhere else. Boots on something solid, a flag, a photo. The truth is stranger than that. There is no version of a Jupiter landing photo that doesn't involve a spacecraft mid-disintegration. We know this because of the Galileo probe's own death. Engineers tracked its descent in real time. The probe's heat shield, made of carbon phenolic material designed to ablate slowly, lost more than half its mass to friction and heat in the first 2 minutes alone, faster than predicted. It was a machine built specifically to survive deep entry, and Jupiter still chewed through it in under an hour. Let's be honest about what a descent into Jupiter actually involves. You wake up, figuratively, because your instruments never sleep, to readings climbing every second. At the cloud tops, temperatures hover around a survivable minus 145 degrees Celsius, but descend just a few hundred kilometers, and that number flips entirely. By 1,000 kilometers down, temperatures exceed 5,000 degrees Celsius, hotter than the surface of the sun. The pressure tells the same story. At sea level on Earth, you experience roughly 1 atmosphere of pressure. By the time a hypothetical spacecraft reached Jupiter's metallic hydrogen layer, it would be experiencing pressures over 2 million times that, enough to crush submarine hulls like paper instantly, with no warning before failure. This isn't a slow, gradual squeeze. There's no moment where you could turn back. The transition from manageable to instantly destroyed happens within a relatively narrow band of altitude. Engineers studying Jupiter probe concepts have noted that any descent vehicle would lose structural integrity long before reaching even 1/10 of the way to the planet's center. Here's where it gets interesting. Jupiter's gravity makes this worse, not better. The planet's gravitational pull is roughly 2.4 times stronger than Earth's. So everything, heat, pressure, your own body, the materials of your ship, gets compressed harder and faster the deeper you go, accelerating the destruction instead of slowing it. And then there's the radiation. Jupiter has the most intense radiation belts of any planet in the solar system, generated by its enormous magnetic field. The strongest of any planet, roughly 20,000 times stronger than Earth's. NASA's Juno spacecraft, which has orbited Jupiter since 2016, was built with a titanium vault specifically to shield its electronics, and even with that protection, mission engineers designed Juno's orbit to minimize time spent in the most radiation-saturated zones, because prolonged exposure would fry its instruments within hours. A human astronaut, unprotected, would absorb a lethal radiation dose simply passing through certain regions near Jupiter. Not from landing, just from getting close. More depth means more pressure. More pressure means more heat. More heat means faster material failure, and faster failure means less time to transmit data before the signal goes silent. Each problem accelerates the next, the way a snowball doesn't just grow. It picks up speed while it grows. By the time a probe reaches the metallic hydrogen layer, it isn't traveling toward a destination anymore. It's simply running out of time before it stops existing as a coherent object at all. So picture the full stack of problems happening simultaneously. Crushing pressure with no floor to stop your descent, heat that exceeds the sun's surface, gravity accelerating your fall, and radiation lethal enough to kill before pressure or heat even finish the job. There isn't one barrier to landing on Jupiter. There are at least 4, stacked on top of each other, each one fatal on its own. Then there's the deeper problem, the one that has nothing to do with engineering at all. Even with infinite technology, immune to heat, pressure, and radiation, you still couldn't land because landing requires a surface, and Jupiter's interior structure simply doesn't include one. Somewhere around its core, hydrogen and helium may blend into a dense, possibly slushy mass. Not a hard boundary, but a smear of matter under crushing pressure with no fixed shape. This changes the entire idea of exploring Jupiter. Every other body we've explored, the Moon, Mars, asteroids, even Venus, eventually gives you somewhere to stop. Jupiter doesn't offer that option. Not now, not with future technology, not ever, because the planet's physical structure makes stopping geometrically impossible. Once you understand this, every other planet looks different. Venus is one of the most hostile environments in the solar system, but it has a surface, and the Soviet Venera landers actually touched it in the 1970s, surviving brief minutes in temperatures of about 465 degrees Celsius. Jupiter offers none of that mercy, because there's nothing waiting at the bottom to survive on. This is why every realistic mission concept for Jupiter, Juno, Galileo, future probes, is designed to orbit, dive briefly, or sacrifice a probe for one final burst of data, never to land. Scientists don't talk about a Jupiter landing because the word doesn't apply. They talk about how deep something can get before it's destroyed. Think about how strange that is. We've sent humans to walk on the Moon. We've sent rovers to drill into Mars. We have plans, however distant, to put boots on both again. But nobody is drawing up plans to land on Jupiter, ever, because the planet itself makes the question irrelevant. It isn't a budget problem or a technology problem we'll eventually solve with better materials. It's a fact about what Jupiter is made of, and that fact doesn't change no matter how far our engineering advances. So here's the strange part most people never consider. We grew up assuming every planet eventually has a floor, a place where falling stops and standing begins. Jupiter quietly breaks that rule, and almost nobody notices, because we've never had to think about a world built entirely from fall. Every other world in the solar system eventually says yes to the question, can I stand here? Jupiter is the only planet that says no, permanently, and means it. You spend your whole life assuming down eventually ends somewhere. Jupiter is the one place in our solar system that proves it doesn't have to.